if we're trying to figure out where we can place the 5 Newton weight so that the system can still be in balance, but we're right on the precipice of it tumbling around, our first hint would be set T1 equal to 0. Because that's going to be the moment, right? Right when T1 is no longer supporting the meter stick, that we're at the balance point. So that's your first hint. So see if you can do the problem from there. Go through your set of steps. So draw a picture showing where the forces are acting. Decide on a location for your fulcrum or pivot point. Set up your chart and flesh out your chart. Generate a force equation. And then generate a torque equation. So we did yesterday. I'll give you the second hint in a minute, but I really think you guys got to battle it out a little bit between you. Maybe talk to your friends and such. Two will end up being all the weight because it's the only thing holding it upwards, right?
So then would I still have the 0.66 for the weight of my object going down?
You could.
Thank you.
So you're, like I said, hint number 2, place the fulcrum at T2 because it's an unknown. But as George just said, we kind of do know what it is. It's the total weight of the meter stick. And by the way, we're getting some fluctuations on the weight of the meter stick, clearly. So it looks like it might be, oh, you're going to love this. It might be 0.67. I'm so sorry to say. That's not going to make much of a difference in your answer, but the fact that you'll have 0.67 to work with, I know you'll love that. So we'll just leave it there. Okay, I haven't come by to see everybody, but I've seen several people, and I think we're making some progress. So let's go ahead and advance through our series of steps real quick. Hint number 1 was to make T1 equal to 0, so we're going to make T1 equal to 0. Hint number 2 is to place the fulcrum at T2, so we're going to place the fulcrum at T2. All right, those hints are now done. Step 1 was to make sure we draw a picture that shows where all the forces are acting on our object. We've done that. Now, we could do the net force part real quick because we could do that right now. Our net force part is going to say that T2 is up and the 0.67 and the 5 newtons are down. But that just tells us that T2 is going to equal the weights that are added to the meter stick. That's worth knowing, and I don't want to forget to do that. I'm just not sure it's necessary for this question. So let's go on to the next part, which is to create a chart. If T1 is 0, I don't think T1 is applying a torque because that force is 0. The weight of the meter stick, though, it is applying a torque. So I will have a torque from the meter stick. And the 5 Newton weight, I think it's applying a torque too because it's pushing down on the meter stick. T2 isn't applying a torque because T2 is at the pivot point. And remember, a torque is only applied if the force is applied some distance away from the pivot point. I want you to imagine, will the door ever open if we push on the hinge? No, you can't apply a torque there because you're pushing at the pivot point. So that leaves us with only 2 torques here, and I do want to remind you that a torque has 3 parts. So let's kind of work it out, knowing that this is a statics problem, so it has to sum to be equal to 0. So our first torque is going to be the meter stick itself. And our torque arm is from the pivot point to where our force is applied. That looks like 30 centimeters. So I'm going to put 0.3, so that's in meters. And aren't we lucky that the weight of the meter stick is 0.67? Yay, we're so excited about that. Now the next part, of course, is to deal with the angle. And right now, our problems have been pretty easy because our angles have been 90 degrees. So this would be the sine of 90. They're not going to stay like that. We're going to have some with some angles in there, but they're not hard. You just have a different angle in there. Now we got to go on to the next one. And we don't know the distance. But that's the point. We're trying to figure out the distance. So I need to put a placeholder here to just let me know that there's a distance there. I'm trying to figure out what that distance is. I'm going to use R because torque arms are R. But you can use any letter you want. You just need a placeholder. The weight is 5 newtons, so I'll put the 5 there. And again, this one is also sine of 90 degrees. Now we do have to deal with direction. And we can just use clockwise and counterclockwise. The real question is, do you want clockwise to be positive or counterclockwise to be positive? So we're going to make clockwise positive. Just kind of saying it out loud and drawing myself a little picture to remind me. Well, I think the 5 Newton weight is causing a clockwise torque. I know some of you are having trouble with that, but if the pivot point is here and you push down here, that's going to cause it to go this way. That's clockwise, right? So that has to be positive. And that means the other one's probably going to be negative too. Any question yet? Go ahead. The distance is, the torque arm is from the pivot point to where the force is applied. We set the pivot point where T2 is at 80 centimeters, but the weight of the meter stick is at its middle at 50 centimeters. So from 80 to 50 is 30 centimeters. Is that okay? Excellent. Well, now it's just arithmetic, I think. So I'll do 0.3 times 0.67, and I'll get 0.201, or negative 0.201, plus 5R equals 0. Yes? This is a completely different way to decide the direction of a torque. Okay, completely different. I'm going to do it all in a different color and everything. And I'm going to erase this. Everything that we've done so far we can use. But what we're going to do is we're going to take and overlay what we've drawn with a coordinate system. Put it right over the fulcrum. Like so. Can you see that okay? And we're going to go positive and positive. So up and to the right is positive. Down is negative, and to the left is negative. Okay? All of our R's are positive or negative. All of our forces are positive or negative. Because our R's are left and right, and our forces are up and down. Ready? Let's deal with this one first. What direction is R? To the left, so that is. So we make that R negative. What direction is the force? Is it positive or negative? So you make the force negative. Go down to the next force. Is that R to the right or to the left? So we make that R positive. Is the 5 up or down? So you make the 5 negative. You see what I've done? Now this works too. Now this is a standard that you can use anytime you want. This standard doesn't allow you to make any decisions though, which is okay. At the end of this, this is saying that your directions are based on this, and it's going to give you a torque. It's going to still do the same thing that we did before. It's going to make your torques that are in one direction positive and your torques that are in another direction negative. And it will work every time too. No right-hand rule required. You'll have to interpret what positive or negative means for your answer though. Does that make sense? Okay. So in this case though, we're in pretty good shape. That'll mean positive 0.201 minus 5R equals 0. So this just swapped positive and negative because it's not allowing me to choose whether clockwise is positive or clockwise is negative. That's the only difference. It's forcing clockwise to be negative. So I still do the same work. 0.201 minus 5 equals 5. I'm sorry, minus 5R equals 0. So 0.201 equals 5R. So R equals, I guess I got to divide by 5, and I get 0.04 meters. So in this question, I haven't changed very much. T2 is still going to be at the 80 centimeter mark, but I'm shifting over the other support so that T1 is now at the, I didn't say that right at all, did I? Thank you. T1 is still at 20 centimeters. I'm shifting the 80 centimeter one to the 60 centimeter mark. So T2 is at 60 centimeters. The weight of the meter stick is still at the middle, 50 centimeters. And I'd like you to tell me, what is T1 and T2? Your set of steps will lead you right to it. Now, I don't really have a hint. I mean, I do, but I want to remind you that nothing changed about the meter stick. Its center of mass is still at the middle, and it still has a weight of 0.67 newtons. You have to pick a place to be your pivot point again. So you have choices. I gave you some ideas of what to do about that. So remember, the best place to place the pivot, because you can place it anywhere, is to eliminate an unknown. You have two unknowns. Okay, look, there's only 5 minutes left. So just hear me out, because I want to make sure we get some closure here. The first thing I want to remind you that is this is still a force problem. A net force equals 0 problem. That's still true. So there's two up forces and a down force. So this is still T1 plus T2 because they're upwards. Minus 0.67 equals 0. That's still true. And that may or may not be useful in a minute. Now, I recommended that you choose a place for your pivot point, and I suggested that you place your pivot point at an unknown. So I think half of you chose T1 and half of you chose T2. It makes no difference. So I'm going to choose T1 as my pivot. If I do that, I eliminate T1 as a torque. How many torques are left? 2. So I see 2 torques, and I'm going to list the torque from the meter stick and the torque from T2. These are my 2 torques. Each torque has 3 parts. So the first part is the distance from the pivot to where the force is. So for the first torque, that's from here to here, that's 30 centimeters. So 0.3. And next is the force, that's the weight of the meter stick. And next, the sine of the angle, that's still sine of 90. Now, if you want to do this the way Ava talked about, with doing the minuses and pluses right now, then 0.3 would be positive because it's to the right, but 0.67 would be negative because it's downwards. So we'll just continue that because that's just as good as any way to figure out one of the positives and negatives. But also that's just saying that clockwise is negative. That's all that's saying. Now the next one is the distance from the pivot point to where T2 is. That's just another 10 centimeters. So I'm going to just put 0.4. It is also positive. But T2 is upwards, so it's positive. So I'm going to put T2 here. And that's also times the sine of 90. This still has to sum to be equal to 0. All good? All right, so that'll be negative 0.201 plus 0.4 T2 equals 0. Any questions about that? All right, I'm going to solve for T2 and get that T2 equals 0.201 divided by 0.4, which I get 0.5025 newtons. But I also have to figure out T1. Excellent. I'm going to plug it into this equation. That's right. So I think it's going to be you. It could happen. So these are our 2 values. Let's see. Is this what we actually have for an answer? Because I don't know. It's been sitting up here for a while. Let's see. So our answers were 0.5 and 0.17. I think we're really close again. So I think that's very reasonable. Now, there's only 1 minute left, So we can't do the next question. But